The next topic that we're going to cover is the mole, which is the ultimate counting unit in chemistry. So the mole is similar to counting units that you're already familiar with. So some examples are that we have the word dozen for 12. Another word for two is a pair. So a mole happens to be 6.022 times 10 to the 23rd. So this is what's known as Avogadro's number. So that is Avogadro's number. And that seems kind of like a random value. So where did that actually come from? Well, this is a really interesting story because this is something that's actually still changing even today. So the prior definition of a mole, so this number, was the number of atoms in 12 grams of pure carbon-12. So that is the old definition. So it was the number of atoms in 12 grams of carbon-12. Okay, so there's a little bit of a problem with this definition in that this definition was based off of the fact that it was based off of another unit. So this gram was really based off of the SI unit, which was the kilogram. So the mole started running into a problem when the definition of the kilogram was changed several years ago due to instability of the actual kilogram weight that was used to define the kilogram internationally. So when the definition of the kilogram changed, scientists realized that the definition of the mole also has to change. And this is kind of a good thing for us because the new definition is actually easier. So the new definition, as of May of 2019, is a mole is exactly, now get ready for this, this is a lot of, I've got a lot of digits for you here, 6.02214.076 times 10 to the third elementary entities of a substance. So elementary entities of a substance. So elementary entities could be atoms, could be molecules. It depends on the substance we're looking at. So based on this definition, in our class, I only really care if you round to those first four values. You can use the entire number if you want, but when I'm doing my calculations, I am going to use 4 significant figures just for consistency across all the calculations I'm doing in this class. So how does one actually use the mole? What is it actually for? So basically, we use it because molecules are really, really tiny. So in any sample of anything, you're going to have a lot of them. And notice 6.022 times 10 to the 23rd. That's a really big number. So that's a lot of atoms or a lot of molecules. So it's basically a way for us to determine how many atoms or molecules we have in a substance. So I'm going to give you an example of some ways that this is going to be used to calculate. But we're going to start first with a value that's a little bit more familiar to you. So if you have 4 dozen eggs, how many eggs do you have? Okay, so that's really simple. You say just multiply by 12. But it gets more complicated when we have a more unfamiliar value, something like a mole. So using this example, I want to show you how to solve this on paper mathematically in a logical and organized way. So we're going to use dimensional analysis and start with 4 dozen eggs. And we want to find the number of eggs. So the units we want to end up with are numbers of eggs. And our conversion factor here is that in 1 dozen eggs, we have 12 eggs. So that's actually going to show us that our units cancel, so the dozen eggs cancels with dozen eggs, and we end up with 4 times 12 to get 48 eggs. So we can do the same thing with moles. So if we have 4.0 moles, so we abbreviate moles as MOL, of atoms, how many atoms do we have? So we can set up our dimensional analysis the same way. 4.0, this time with moles of atoms. And we want to get to just atoms. So for every 1 mole of atoms, in 1 mole, we have 6.022 times 10 to the 23rd atoms. We can cancel these units. So if all the units cancel and we end up with what we were trying to solve, we know we probably set up the problem correctly. And you can go ahead and plug that into your calculator. I have already solved it, so the answer is 2.4 times 10 to the 24th atoms. Notice that I used 2 significant figures, and the reason is because this value has 2 significant figures, this value has 4 significant figures, and when we're doing multiplication, we round to the number of significant figures that the number with the fewest sig figs had. So this one only has 2, 4.0 is a 2 sig fig number, so we have to round our final answer to 2 sig figs. And remember that the 10 to the 24th is not significant, those are just placeholding zeros. So now that we've learned how to use the mole to figure out the number of atoms in 1 mole, or in a certain number of moles, this leads into a definition that we use all the time in chemistry, and that is molar mass. So this is the mass of 1 mole of atoms for an element. And this is the same number as the atomic mass, except we use different units. So remember, for atomic mass, we used AMU, which were atomic mass units. For molar mass, we use grams per mole. We abbreviate that as either grams over moles with a horizontal dividing line, or you might see it with a diagonal dividing line, like that, grams per mole. Both of these mean the same thing, and when we talk about it, we vocalize it as grams per mole. And we can use this value to convert between grams and moles. So what that means is if we take a mass of some amount of substance, not only can we figure out like how many grams of something we have, but we can actually figure out how many atoms are in that sample. So for example, let's say that you have some pencil lead, and pencil lead isn't actually made up of the element lead, it's made up of something called graphite. And graphite is pure carbon. So imagine that we have a sample of pencil graphite that weighs 0.0265 grams. So that's 0.0265 grams of carbon. And I want you to find the number of moles of carbon you have. So when we're doing dimensional analysis, we always want to start with the number that's given, which is 0.0265 grams of carbon. And also, you always want to write out all of your units just so that you don't get confused. Now we have to line up our units, so grams of carbon will go on the bottom, and what we're trying to convert to will go on the top. So moles of carbon. And the reason that we know we can convert directly between grams and moles is because we have a molar mass for carbon. And the molar mass of carbon equals 12.01 grams per mole. And you can get this by looking at the periodic table. So we have 12.01 grams of carbon. So notice the 12.01 goes with the grams. So we have that many grams in 1 mole of carbon. So go ahead and solve that on your calculator. So you should get 0.0265 divided by 12.01. These units cancel. So we're going to be left with moles of carbon, which is what we're trying to find. And when we simplify that, we get 2.21 times 10 to the negative third moles of carbon. Okay, so the next thing I want you to do is I want you to find out how many atoms of carbon are in this sample. Oops. Okay, so based on the example that we did before between converting between moles and atoms, I want you to solve this problem and then put your answers in the comments section. So the last thing I want to go over in this video is when to use Avogadro's number, because that's something that I've noticed students get really confused about. Students know that, oh, we need to use this number 6.022 times 10 to the 23rd, but how do we know when to use it? Okay. So this number is only going to be used when we're converting between moles and either atoms or molecules, or whatever object you are trying to measure. In chemistry, it's usually atoms or molecules. So we do not use Avogadro's number when we're converting between moles and grams. So not for converting between moles and grams. In that case, we want to use the molar mass. So I'm going to draw this out visually for you. So if we're starting at grams and we want to get to moles, that's where we're going to use the molar mass. So grams to moles, we use molar mass. And then if we want to convert between moles and atoms or molecules, that's when we can use Avogadro's number. So that's when we're going to use 6.022 times 10 to the 23rd atoms over 1 mole. And then if we want to convert back the other way, if we want to go from atoms or molecules to moles, then we're going to basically flip that fraction, and we're going to have 1 mole over 6.022 times 10 to the 23rd atoms, or molecules if that's what you're trying to solve for. And then finally, if you want to convert from moles to grams, then you're going to use the molar mass again. So notice, you're never going from grams directly to atoms or molecules. You have to go to moles first before you can convert between grams and atoms and molecules. You always have to pass through moles. So let's do an example of this. So here's our practice problem. So a piece of silver jewelry contains 2.71 grams of silver. And silver, remember, that's one that the chemical symbol doesn't line up with the English word for silver. So the chemical silver symbol is Ag. How many silver atoms does it contain? Okay, so here's how I like to organize these problems. So first, I like to identify, what am I trying to find? We're trying to find the number of silver atoms. Then I like to identify what information we already know. So we already know that we have 2.71 grams of silver. And we know that 1 mole is equal to 6.022 times 10 to the 23rd atoms. So what other information are we going to need in order to solve this problem? Because we have grams, we need to get to atoms, so somewhere in there we need to convert to moles, which means that we also need the molar mass of silver. I'm going to abbreviate that as MM. So the molar mass, I'm just going to tell it to you. You would look it up on the periodic table, but it is 107.87 grams of silver. Oops, grams of silver in 1 mole, so that is grams per mole. So here's our strategy. We're going to start with the info that we know. So we know we were given 2.71 grams of silver. You definitely want to start with the unit. If possible, you want to start with the unit that isn't a fraction. It just makes the problem a lot easier to solve. So we have 2.71 grams of silver. And we know we can't get directly to atoms. We're trying to find atoms, but we can't get there yet. We have to convert to moles first. So in every 1 mole of silver atoms, we have 107.87 grams of silver. And it's really important that we line up these units. So notice how this unit will cancel with this unit. And now that we're at moles, now we can use 1 mole of silver, and we know how many atoms are in 1 mole of silver. We know it's 6.022 times 10 to the 23rd atoms. And we also know that this unit will cancel with this unit. We're left with atoms. That's exactly what we were trying to find. So as long as we plug things into our calculator correctly, we've probably solved the problem correctly. So I'll give you a moment to plug that into your calculator. And the answer should be 1.51 times 10 to the 22nd silver atoms. So notice our significant figures. We used 3 significant figures here. So that's because this value has 3 significant figures. This value has 5. This one has 4. Since 3 significant figures is our fewest, we have to round our final answer to 3 sig figs.